All right, I'm going to tell the story of how we came to discover that it snows on Mars. And so I'm giving away the conclusion with the first slide. So the background is that for the past over 40 years, there's been a program of atmospheric research at York University, and it's all been conducted on planet Earth up until recently. And for the most part, we install our equipment in confined spaces like airplanes, and in this picture you can see a plane landing on the polar ice cap, and you can see an aircraft that's at a height of about 15 kilometers in tropical Australia, and one in the desert in Australia, and also in a forest. We were studying forest fires in this case. So we like to go to very inconvenient places, and so we send our graduate students even up to close to the North Pole in icebreakers. We have a laboratory on top of the Amundsen icebreaker. You can't tell very well in that picture, but that student was smiling, and that was probably the last time I've seen him smile. So we've been all over the Earth, and so we had to look further to continue on the theme of going to inhospitable places. So we looked to our closest neighbor, which is Mars. And we were very fortunate to be able to take part in a NASA mission to Mars. So just looking at the planet, this is an image from the Hubble Space Telescope. Right away you can see, looking at the planet, there's a lot of white in there around the edges here. So around the night side, looks like clouds. And if you look at the infrared radiation coming from the planet, you can see the temperature at the surface is too warm for carbon dioxide ice to form. The atmosphere of Mars is mostly carbon dioxide. And so you get a pretty good idea that there are ice caps, there are clouds, that there is a hydrological cycle on Mars. And I should say from the outset that any mission to Mars, the most profound thing that could be discovered is that there are signs of life, that there's been life in the past, that it could support life. So that's the most profound thing that could be discovered. So that's basically the driving objective of any Mars mission, at least the ones that are sponsored by NASA. And okay, so we were very fortunate. We were invited to be part of the NASA Phoenix mission to Mars. It was launched in August of 2007 and landed on the 25th of May in 2008. Before I continue, I should tell you that, okay, this is a picture of the sign, the billboard outside the Mission Operations Center in Tucson, Arizona. And I can tell you at the launch, I was invited to a party as a VIP. So I was leading the Canadian team, and I thought I was quite special at this party. And I showed up, and there was over 2,000 people there as VIPs who contributed to the project. And Bruce Willis was providing the entertainment. And it was, so there are a lot of people involved in a project like this. So this is the billboard outside the Mission Operations Center. And the project was unique in that it was run from a university, from the University of Arizona. So the overall principal investigator was Peter Smith at the University of Arizona. And however, Jet Propulsion Laboratory, this is where most of the engineering work was done for the spacecraft. And that really is the biggest achievement in any of these missions, is landing a spacecraft on another planet. There are so many, millions of things that can go wrong. Any one of them goes wrong and the mission doesn't work. And so a lot of credit has to go to the engineers, all around, even with the instruments. It's really an achievement in engineering. And so York is in here, and our engineering partners were McDonnell Detweiler Associates Space Missions in Brampton. They built the instruments, we designed them. And Optech, a company that was formed by a professor at York University many years ago, and he was my PhD supervisor, and all of this really grew out of the research program that he started at York in 1968. And then a number of different universities associated with all of the different instruments on the spacecraft. Okay, so first of all, up until the launch, up until we delivered the instruments to launch, we were just the Canadian team working on our instruments, a lot of challenges, and we didn't interact that much with the rest of the mission. And at launch, it was very impressive. So we went to the launch site at 4 o'clock in the morning. It was launched in darkness. It was very impressive. We go back to the hotel, and I turned on the NASA station at the hotel afterwards, and they were making a slight correction in the course of the spacecraft already, because it was aimed directly at the landing site on Mars. And so just in case there was a glitch on the way there and the mission wasn't going to work, they aimed it slightly off of Mars, so it would miss Mars and not crash into it for no reason. And it was that accurate. And you could say that, well, all it takes is a boost of 3 kilometers per second from the Earth, and it goes into this elliptical orbit that intersects Mars 9 months later, and that's all there is to it. That's a undergraduate exam question in planetary physics, and it's fairly straightforward, but it is really quite impressive. And then the landing is the part that was kind of shockingly impressive, because it went exactly as the animation I'm about to show you. So this was an animation before the mission, and this included all of the events that had to occur to land successfully and for the mission to get going successfully. So I thought I would show this, and this is pretty well exactly as the landing went. So we did many rehearsals leading up to the mission for operations, and we'd started all the time with a simulation of what was going on in the landing. And so everything for us, all of our input was as if there was an actual mission going on. So we would hear all of the events in the landing. And so when it actually happened, it was surprising in that there was no difference. So here's the spacecraft approaching Mars. Starting to enter the atmosphere. Heat shield is burning away, dissipating a lot of energy. Parachute deploys. So far, so good. The part that really scares me is coming up. Drops the heat shield. Landing legs go out. Now this part coming up very soon is what really got me. So we would hear this happen there. It's free fall. Turns on the thrusters for a few seconds. Lands on Mars.
Oh boy.
In the actual landing, the spacecraft actually bounced and landed again. And right away, the solar panels get deployed. So it was sending back this information with a time delay to Earth, and we were hearing all of this. So this is all just an animation. So that camera worked very hard, taking hundreds of pictures every day. That's the Met mast. That's where we measure temperature and wind. There's the arm. The arm was the most important part of the mission because it would dig into the soil and pick up samples to put in instruments for chemical analysis. And that was the first priority of the mission. So it was very difficult to dig into the soil. The Canadians all knew this would be difficult because we know what soil is like at temperatures of -60. The Californians apparently thought it would be easier. And then delivering the sample to instruments that would analyze the chemical composition of the soil, with the first priority to find out if there were any organic molecules. That doesn't mean there's life, but it means that they're building blocks. And here's the lidar, and that was the instrument that we provided from Canada. That was led from York University and built in industry, and the funding was from the Canadian Space Agency. So once the spacecraft landed, actually, if you have an instrument on board and the spacecraft lands, it's kind of like you get more nervous. It's something to celebrate, but now it's like, oh, now it's going to have to work, or it's going to be quite a disgrace. And it was kind of like when I was a kid arriving at a hockey tournament, and I wasn't quite thinking about playing hockey. You walk into the arena, and you hear all the sounds of a game going on, and you realize, oh, I'm going to have to get into this now. And so, then we were up. Another picture that came in right after landing was from orbit. Now, so this is just showing, so when we arrived at Mars, there's a number of other spacecraft in orbit. Would it be better if we turned off some lights? Is that easy enough to see? Is that better? Okay. So when we arrived at Mars, so here's the Mars Express, a European spacecraft that was in orbit around Mars. This is Mars Odyssey here, another American spacecraft that had been launched back in 2001 or so, and the Mars Reconnaissance Orbiter. And it just so happened when Phoenix was coming down to land, to enter through the atmosphere, the Mars Reconnaissance Orbiter was right there. And so they aimed the cameras at the landing site, or near where Phoenix would be landing. And this is one of the photographs. So in the background, this is a crater called the Heimdall crater. It's gigantic. It's about 20 kilometers across. And now this dot here, blow that up, and here we have the spacecraft and the parachute, actually. And you can actually see the cables in between the spacecraft and the parachute. So it's about 20 kilometers in front of the crater right now. It's coming down through the atmosphere, so it's pretty high up. And so it's not landing inside the crater. It's landing away from the crater. But so that was very impressive as well. So this is a satellite orbiting Mars, and it can see these cables that are half an inch in diameter or less. Okay, so this is another photograph, the same instrument, photographing the surface. Here we have the lander here, heat shield, and the parachute all together on the surface. Another close-up of the nice, shiny, brand new spacecraft on the surface of Mars. There's the spacecraft, there's the solar panels. And then there it is. So this is a picture from the camera on board the spacecraft looking out over the deck of the spacecraft and over the terrain. And so that was really quite impressive. And this is the main instrument supplied from Canada. We supplied the temperature measurements and the pressure measurement, and those are fairly straightforward. And the real experimental instrument was a lidar, which is under its blanket here. We snuck in the Canada word mark here, which they weren't too happy about. Then they had to Velcro on an American flag. And but this was so of all the instruments, one of the reasons this mission was selected was because it had a heritage. It was planned. It was a planned mission from several years earlier. So all of the instruments were already available, had been tested, and there would be a lot of savings in that respect, except for the lidar. So this was a very experimental instrument to put on a spacecraft. It's very difficult. It's based on a laser. And in the end, the payload manager called the lidar like the riskiest component of the mission, the highest technology. So we had a lot of reasons to be worried, and I'll show you why in the coming slides. And don't worry, it's a good ending. So this is just another picture of the artist's conception. Looks remarkably similar to the terrain as we found it on Mars. And okay, so the main scientific reason the mission was selected was this result from the gamma ray spectrometer on one of the satellites orbiting Mars called the Mars Odyssey mission. From the surface and how they're attenuated by interaction with hydrogen in the surface. And the interpretation of these results is that they're observing water. So the colors here, the red is a lot of water, the blue is very little water. And the interpretation was all this part here, this is water under the surface. So looking down on Mars, that all looks like a desert, brown and red. And so this is saying that there's a lot of water actually on Mars. When I first taught a course on planetary science, one of the things was we'd say, well, what happened to the water on Mars? And this result implies that, well, a vast amount of ice under the surface here. And so the first goal of the Phoenix mission was to confirm this result. in situ, to actually dig down and find this ice under the surface and confirm that it's actually there. And the reason it's very important is the overall objective of the Mars program is to look for conditions of habitability. And water is the first condition for any habitability for life in the past, in the future. And so that was our goal. And okay, so there's our landing spot away from the polar ice cap over here. And it's all brown. It's desert. It's brown and red. That's what the Earth would look like without any life or water. And so throughout the presentation, I'm not a pure planetary scientist, so I've worked on Earth most of my career. And so I refer everything to Earth. So we take our knowledge of Earth and apply it to Mars. It's not the other way around. Sometimes planetary scientists like to say we're learning about other planets that teach us about Earth. For us, it's really we've taken our technology from Earth and our knowledge and we're applying it to the study of Mars. And so this is one example. On Devon Island, for example, in the Canadian Arctic, you can see the terrain here has this pattern of these polygonal shapes. And this happens when you have ice beneath soil. So in the summertime, the ice expands. In the wintertime, it contracts and it cracks. And then some of the rubble falls into the cracks, and then it tries to expand again, and it can't. And it results in this pattern. And now look at this picture. This is the terrain around the Phoenix spacecraft. That's one of the first photographs to come back from Mars in the Phoenix mission. It has this same sort of pattern. So that evidence was there already that it does look like Earth wherever you have ice beneath soil. However, it took about 1 hour to confirm that there was ice beneath the soil. And so this is a picture right after landing. There's a camera at the end of a robotic arm, and they use it to look under the spacecraft just to make sure that the feet were sitting in a stable fashion. So you can see the thrusters here for landing. So while it was landing, these thrusters blew away the dirt to reveal this rather flat and bright surface. So if that is not ice, then it's something far more profound than ice. And you get the impression, looking at this, that you could take a snow shovel and shovel away the dirt, and you'd have yourself a skating rink. And so already, for the scientists, for us, that was it. We confirmed there was water there. But the higher administration at NASA wanted proof. They wanted a chemical analysis to prove that the H2O molecule was discovered, not just something that looks like ice. So the mission carried on. We didn't pack up and go home then. And so we had the robotic arm. So the idea was that would dig into the soil and get samples. And the first goal was to sample some ice and prove that it was ice through chemical analysis. All right, so this is the first trench that was dug. They were prepared to dig 1 meter in depth in the soil. And they got about 1 inch or half an inch before hitting this. Well, we call it permafrost. It's actually like bulk ice in some sense, but we hit ice. So we couldn't dig much further than that. And so looking at this picture, they were calling it white stuff. So the NASA wouldn't let us say ice or water, and so we had to say, well, there's white stuff there. And the late night talk show hosts really had a good time with that. And so looking at this, so how are we going to prove this? And it was really difficult to get any piece of ice here. It would sublimate. Once it was exposed to the atmosphere, it would just evaporate away. It would sublimate, and it wouldn't be stable. However, looking at this picture, you see a couple of chunks here, over here, of the white stuff. And this is Sol 20. A Sol is a Martian day. So 4 days later, and a Martian day is 24 hours and 40 minutes. So it's something like an Earth day. And 4 days later, these chunks had disappeared. So again, so what's happened there is they've sublimated. They've evaporated into the air. It's a bit warmer up and when exposed to the atmosphere. And these sublimated away. So that was further proof that, for us, for the scientists, that this was indeed ice.
What's the surface temperature?
It was negative 30 during the day, negative 80, negative 90 at night. So these temperatures, ice is stable, but it's not carbon dioxide, because carbon dioxide would definitely evaporate away at those temperatures. Carbon dioxide ice is only stable at like negative 150 Celsius at that pressure. Okay, so this is the end of the mission. So this is, the after the battle was over and all of the digging. You could see that the geologists on the mission were trying to find a place to dig deeper down, and basically, so each time there was samples being taken and delivered to instruments for chemical analysis. Okay, and so you can see a bit of that on the MECA instrument. So this instrument, microscopy, electrochemistry analyzer, that's what it stood for, MECA. It was really a lot of different, it's like a Swiss Army knife instrument. It had about 10 different things going on, and you could usually involve delivering dirt to the instrument into these cells. And these were cells that actually did wet chemistry. So the dirt was dumped into a cell, some water was put in the cell, and they were able to analyze the composition of the soil. And the most surprising discovery was they discovered the soil contained perchlorate. So that's chlorine with 4 oxygens around it. It's toxic on Earth. It's known to be toxic. It's very explosive and it's used as rocket fuel. And when you burn perchlorate, it produces oxygen. And also, so it has some very practical implications, being on another planet, and you can use it for rocket fuel and producing oxygen. But it can also control the water on Mars. It has a great affinity for water. It's used as a desiccant, as a drying agent in the lab quite often. So that was one of the big surprises from the mission. Okay, so the Canadian team, our main challenge was to provide the lidar instrument. Lidar means light detection and ranging. Radar means radio detection and ranging. So radar means radio detection and ranging. So a radar is just a lidar that uses radio waves. A lidar uses laser light. So we're emitting pulses of laser light and detecting what gets scattered back. So when you see a police officer on the highway pointing that device to determine your speed, usually that's a lidar in there. That's usually a laser beam bouncing off your car, and they can see where the car is as a function of time and get the speed. And so it's fairly straightforward. We emit a pulse of laser light. So at the heart of the system, there's a laser. We emit a pulse of light with the laser, and this goes directly up into the atmosphere. It scatters from the particles in the atmosphere. In the case of Mars, it's dust and cloud ice crystals. And then we have a telescope to collect the light which is scattered back. And then we detect it and record it as a function of time very quickly. And we know the speed of light, so we know how much light was scattered from different heights. So we get the height profile of material in the atmosphere. This is what it looks like. Here's the telescope for the receiver. This is the laser. It's the heart of the system here. That's where all the challenge was, the telescope. There's a detector under here. And of the specifications, the two that are most important are 6 kilograms and 35 watts. So that's the budget of mass and power that we were given to make use of on the spacecraft. We couldn't go above that. And both those numbers are a factor of 10 smaller than what we could achieve in the laboratory here at York. So we build lidars just like this all the time to put on airplanes and in trucks and in the lab, but they're a factor of 10 greater in mass and power. And all of the individual components have to be pre-selected as things with heritage in space, or they're qualified to go into space. We couldn't just take anything off the shelf and launch it on a spacecraft, and it wouldn't even get through testing to start with. So that's where industry comes in. So at York, we can build instruments, but we don't know how to build an instrument to put it into space. There's a lot of know-how, many decades of experience that goes into that. So the people who build the Canada arm on the space shuttle are the people who built this instrument. And so there's a lot of know-how that went into that. However, the engineers in industry don't know anything about building a scientific instrument. So it took a long time for us to start working together very effectively. There are a lot of arguments at the beginning of the mission. It's just natural. This is just looking in at the laser. This is where all our trouble was in getting the instrument ready. And I won't go into any detail here. But in the end, we had a lot of trouble because the temperature of the instrument changes quite a bit while it's running. And it came down to putting a lot of special glue onto one of these optics over here to stop it from moving as the temperature changed. Okay. So this is what we build at York. The same instrument, or the same instrument characteristics. This is in an aircraft rack, and here's the laser, a mirror, directs it directly up out of the airplane when it's in the airplane. This is the telescope, detectors over here, and the electronics. So this is the instrument that weighs a factor of 10 and uses a factor of 10 more energy than the one that went to Mars. So that we use this for testing the space qualified instrument, and we use this for going into the field to take measurements in conditions that are similar to Mars to help us understand the results that came back from Mars. All right, so here we were. This was probably September of 2006. We're all looking very young and smiling, and we're just about to embark on testing the instrument. Here's the Phoenix instrument that went to Mars. And so in our plan, we would be running our lidar from York, comparing it against this instrument. This is at the David Florida Laboratory in Ottawa. And it would all be great and fun. And about 8 months later, after working 80 hours a week or 30-hour shifts and being in a constant crisis, we had a lot more gray hair. You can't tell from this picture. But this is also a nice picture. So the space exploration in Canada is funded actually through Industry Canada. And this is the sort of picture they like to see, because what we have here is 4 engineers and 4 scientists working on a very difficult problem together. And all of us learned a lot from working together. So I learned so much in this mission. I'm a totally different person with a totally different perspective and different skills, and that's true of everyone. So, in this picture we have scientist. I guess I'm an engineer and a scientist. This is Mike Daly, the chief engineer, who is now a professor at York in space science, and engineer, and engineer over here. And so the whole idea here is to get scientists and engineers working together on very difficult problems. And this is where we spent our time. This chamber, this is a thermal vacuum chamber. So inside this chamber, we create the same conditions as on Mars. Pressure is about 1/100th of the pressure in this room right now. Temperatures down to -90, -100 degrees Celsius. And so we would have the lidar viewing out this window and then reflected across the room and then out into the atmosphere. So we had the York lidar in here looking up into the atmosphere, and the Phoenix lidar over here. So we could take measurements in the Earth's atmosphere at the same time while the instrument was actually in Mars conditions. So that's how we tested it. And so this is the atmosphere above Ottawa over the winter of 2006, 2007. Dalhousie University were helping us. They had a very powerful laser. So these are laser beams up into the atmosphere. Okay, so I'll describe one problem we had. There are many problems we had to solve, at least a dozen of them between Christmas and March of 2007. Every one was a crisis, and it always seemed like the mission was over. And we wouldn't have even found these problems if it didn't take so long to solve this one. So this cone here, with the blue at the top, this is depicting the field of view of the telescope. So it's looking out with a very narrow field of view. And the green here is the laser beam. So we had to have the laser beam aligned to be within this field of view. And the problem was there was no way to dump the heat of the instrument. In the lab, we have water running through the instrument, take the heat away. We can keep the temperature stable. On Mars, we don't have the mass and the energy to do that. So the instrument just heats up as we run it. So there's 35 watts dissipated. So it would heat up in half an hour from -40 degrees to 0. While it does that, it expands or contracts depending on whether it's heating up or cooling down. And then it twists. And it's very difficult to keep the outgoing laser beam aligned within the field of view. And this is just a few tenths of a degree. And so that was our problem. So the first time we tested it, the laser beam ended up way over here after it just going from room temperature down to -90. And we had a very serious problem. So in the end, we were able to arrange it so that between -40 and 0, the beam stayed within the geometry of the field of view. So it seems very simple, but that took us months, because every time we had to change something, we had to come out of the TVAC chamber, put it back in the TVAC chamber, take a day to pump it down and equilibrate thermally, test it, it didn't work. And then another day to take it out of the chamber and make a change. And so while we were doing this, we kept encountering other problems. Sometimes little components on the electronics boards would actually pull apart because they were expanding and contracting at different rates. And so we found all these problems over a period of 3 months that we wouldn't have found if it didn't take us so long to solve this one. So we were lucky. it was a good lesson learned that sometimes finding a problem and taking a long time to solve it is a good idea, because you find other problems. So the point there is we had a lot to worry about. Once the spacecraft landed and all the engineers were very successful, it was our turn. And here we are with the first data from Mars is about to come across the computer screen. And, 4 years of work, pretty well, nothing but that. And, we're wondering whether we're about to watch our careers go down the drain. And so there we are. Looks like we're watching a hockey game. Yeah. We could be. We closed the door and didn't let anyone else in, but there was a window there and someone took a picture. We were expecting a lot of tears, and actually it worked. We were quite pleased. So this is the most positive result of a mission to Mars is a dozen very relieved people. So we went from the most nervous people you could find probably to the most relieved. And so that lasted, a few minutes. We had to get right to work as soon as things were working. So we were very happy. So we had the next 5 months to explore Mars and to apply everything we know and do to discover what's happening on another planet. Okay, and so this is one of the people with the camera pointed it straight up into the atmosphere of Mars to see if we could see the laser beam. So this was made into a bit of a movie, just a series of images. And I'm not sure if you can tell, but so here, this is the laser beam in the atmosphere of Mars. There's a cloud up here. You can see it's a little brighter at the top. You see the odd sparkle in the beam, which is probably ice crystals that were falling down to the surface. And so I'll show you how the measurement works. So a pulse of light is going up through the atmosphere, and it encounters particles in the atmosphere. These are actually little images of ice crystals. And light gets scattered in all directions, and the light that gets scattered back, we detect. So sometimes I'll talk about extinction, or it's really just the shadow behind the particles. And if I say extinction coefficient, it's basically the rate at which the light pulse, its energy is diminished with distance through the atmosphere because of this scattering. And it's simply just proportional to the amount of material in the atmosphere. So you can consider it as the density of particles or the total mass of particles. And if I say backscatter, that's just the amount of light that's scattered back per unit length. Again, that's just proportional to the amount of material in the atmosphere. And this is what the signals look like. So this is what we were hoping to see on that computer screen. And that's what we did see. And so this is height. This is the signal strength. And you see we get signal. So this is the number of photons backscattered per unit distance through the atmosphere. So this is basically all proportional to the amount of dust in the atmosphere in this case. So this is the strength of the signal coming back from the atmosphere. I won't show too many graphs. And this is what we derive from it. So this is what I call the extinction coefficient, but this is basically the amount of material. So in this case, there were no clouds. It was just the dust in the atmosphere. So the atmosphere of Mars is mostly dust in terms of what you see in sunlight being scattered in the atmosphere. So this is extinction coefficient. It's proportional to the amount of dust. And so what do we do with this? So, okay, there's dust. It's decreasing with height. And there's a lot more dust closer to the ground than there is higher up. And so we have to compare this to what we see on Earth. So I can tell you on Earth it looks like this as well. Because if you're in the middle of Australia or in the American Southwest, during the day there's a lot of turbulence, convection, and wind that picks dust up from the surface. So in Tucson, Arizona, it's very dusty, for example. And then, so this dust mixes with turbulence up to a height of about 4 kilometers. And it looks like it's doing that on Mars. This is another case. This is just our dustiest day on Mars. I'm going to compare this to Australia in a minute. So a lot of dust from the ground up to a height of 4 kilometers, and then less above. And this is called the atmospheric boundary layer. It's where you get a lot of, so when you're landing on a flight, when you're approaching an airport in the summer, where it starts to get bumpy, is where there's a lot of convection from the ground and a lot of turbulence because of the shear near the ground. But this also mixes material up through the atmosphere. And so it's looking like that on Mars as well. We also looking at the pictures from orbit, so there's various satellites orbiting. We can compare, around the time we landed to a little later, and you can see that there was a lot more dust earlier on in the atmosphere. So we know already there's dust in the atmosphere. And okay, so to understand that, there are places on Earth that look like Mars, and one is the interior of Australia. And I already do a lot of work in Australia. Some years I spend half my time there. And so I have colleagues in Adelaide, Australia, down here. And so we took our equipment, our prototype of the Mars lidar, and up to a place called Mularina in the Simpson Desert. So there was a station there. It was kind of an oasis area with some shacks for previously when it was a cattle and sheep farm. And it's changed quite a bit since the old days, and it's mostly desert now. We had a place to stay there, and there we are. And so we had an airplane. So we had the lidar on the ground taking measurements, and the airplane flying through the atmosphere, getting actual in situ samples. So then we can compare what we measure with the lidar to what's actually in the atmosphere. So the first thing we needed to do was validate the measurements. And we had to write a report and prove to NASA that we understand our measurements. And that's when we say we're measuring this much dust, we have some validation from Earth of what we're measuring. And so here's the wing, looking down the wing of the airplane, instruments on this pod here to sample the dust in the atmosphere. We're down here in our RVs, taking measurements, looking upward into the atmosphere. We have the lidar in one of those. And okay, the area looks like Mars. It's remarkably similar. This is a dust devil, tiny little, kind of a small tornado. When you're in the desert in the middle of the day, you have these tiny tornadoes that come by all the time, and they don't lift you off the ground, but you'll get dust in your ears and your eyes, up your nose and stuff, and you know you've been hit by one of these. But this is the mechanism on Mars that lifts a lot of dust into the atmosphere as well. So we were happy with that. We had a dust storm, and that was very exciting. That happens on Mars as well. And okay, so this is what it looks like, taking measurements in a desert with a lidar. So this is from the morning, noon, 5 p.m. And the color here, this shows the backscatter coefficient, or the amount of dust we're measuring in the atmosphere. So what's happening is the sun comes up, the surface warms, it warms the air rises. And so it's starting to pick up dust. There's a lot of wind and shear and turbulence, and so the convection picks up dust and lifts it up higher and higher up to a height of about 4 kilometers. So in the middle of the day, we have this dust all the way up to 4 kilometers. And the black line is where the airplane was flying, above the lidar. So here's where it's spiraling down around the laser beam of the lidar. So that's what helped us to validate the instrument. And so this result just shows that our measurements are meaningful. So the red line is the lidar measurement as a function of height. The black line is the aircraft measurements. And so we could show the instrument does work, it's valid. And, but the other thing that's very interesting is if we compare our measurements over Australia to our measurements from Mars. The thick black line here is the distribution of dust with height as measured on Mars from ground up to a height of 7 kilometers. So this is the amount of dust in the atmosphere. And the dashed line is Australia. So up through the boundary layer where there's a lot of turbulence, a dusty day on Australia, above Australia, is very similar to a dusty day on Mars. So that's what we learned about the dust in the atmosphere of Mars. And that's the way the atmosphere looked for the first 70 days of the mission. So after a month of this, it was kind of, okay, hopefully something's going to happen soon. And looking down at the atmosphere at Mars, so this is a photograph from before we landed. That's the polar ice cap. There's some snow around the outside. If you look a few months later, it's a bit different. So all that white stuff, which we know is water ice, had disappeared into the summer. So we can see just from images of Mars that there is a hydrological cycle. There's water in the poles that sublimates, evaporates into the air in the summertime, then goes back to the poles. And it moves from the southern hemisphere to the northern hemisphere and back. And so there is water being moved around. But it has always been assumed that there is no precipitation on Mars. For some reason, people had assumed previously that since the atmosphere is so thin, that the ice crystals that form, if they did, in clouds on Mars would be so small that they would just stay suspended in the air and they wouldn't precipitate or snow to the surface like on Earth. So this is the temperature, the minimum daily temperature and the nighttime temperature since we landed. So it warmed up at first. So we landed right before summer solstice, right before midsummer. So summer solstice on Earth is June the 21st, and during our mission, actual summer solstice on Mars coincided with June the 21st. So it warmed up to that point. So all of the water at the surface is going into the atmosphere, it's warming. Then it started to cool down for the rest of the mission. And at some point here, about 70 days into the mission, we started seeing clouds as the atmosphere cooled. This is just a 1 day of temperature measurements on the lander. And so this is near the end of the mission. So the maximum temperature during the day then was negative 40 degrees at noon. And around midnight, just slightly after midnight, down to negative 98, close to negative 100. And then back up to negative 40. All of these variations here, that's due to turbulence and convection through the day. So that's a very large swing in temperature. But it's similar on deserts on Earth have a very large swing in temperature as well, as there's very little water to provide a blanket, a thermal or a greenhouse effect. And this is what our measurements would look like in this case, in the middle of the night. So normally we just see dust. Extinction coefficient, it would just be the amount of dust through the atmosphere. It'd be pretty well constant up through here. But then after about Sol 70, 80, we'd have this big enhancement in the amount of material doing scattering in the atmosphere at a height of 4 kilometers, the top of the boundary layer where there's turbulence, and at the ground. And this would only happen at the coldest part of the day. So this is a cloud for us. We're pretty certain that that was a cloud. So we have what would, in Yellowknife, this cloud at the ground. It's fairly thin clouds. In Yellowknife, you'd call this an ice fog. We don't really get ice fogs in Toronto, but it's an ice crystal cloud near the surface. And this is a boundary layer capping cloud up here. So these are the coldest parts of the boundary layer. And this is what the measurements look like. Part of the strength of the lidar, part of its usefulness is that it runs continuously in time. So it sits there running while the atmosphere is drifting past. So we kind of get a cross-section or a side view of the atmosphere looking at it. So the lidar shows us the structure of the cloud, like the outline of the cloud and the internal structure as it drifts past. So this is time. This is 1 hour of measurement as a function of height. And the colors here, red is a lot of scattering, black is very little scattering. So we can see the outline of this cloud up here and the fog near the ground. And what's interesting are these structures here. So this stuck out to us. So the next figure, I'm just going to plot it in such a way that we can see this better. Okay, this is the same thing. Now just looking at the upper cloud, you see the outline of this cloud and the structure inside the cloud. So this is like looking at a side view of the cloud or cutting through the cloud, looking at it. And so what's very interesting to us here are these streaks, these vertical streaks here. So this is a signature of precipitation. When you're taking lidar measurements or radar measurements, that's what it looks like. So what we have here is ice crystals formed. This cloud formed at about 1 a.m. And ice crystals formed, and then they dropped down through the air. In this case, they dropped down from 4 kilometers to 2.5 kilometers. And given that it took 3 hours or 4 hours to drop down this distance, we know the fall speed, we can estimate the size of the particles, and that they have a radius of about 35 microns, 35 millionths of a meter. Now, this is very similar to what we observe with cirrus clouds. Now I'm bringing it back to Earth and comparing to what happens on Earth. So those measurements look exactly like what we see when we observe cirrus clouds on Earth. So cirrus clouds are these high wispy clouds. See them mostly in the fall, summer, well, all year round. Half the time you see these things. And you see these wispy trails coming out of them, comma-shaped trails. What's happening here is you have ice crystals form in the cloud, and then they fall through the atmosphere as they grow. And then there's some wind shear. So the wind up here is moving faster than the wind down here. So as the particles fall into the slower wind, they form this, they get drawn out in the horizontal. So now here's an example of a measurement below some cirrus clouds in northern Alberta. We were actually flying around looking for forest fire smoke, but we flew beneath some cirrus clouds. And again, so we have, this is the outline of a cloud that we're seeing. This is distance now, we're in the airplane. and so we have ice crystals form at the top, in this case about 13.5 kilometers in height. And we have these vertical streaks. This is where ice crystals are falling down through the atmosphere, like in that picture I'd just shown you. And so when we see something like this, we're fairly certain what's going on there is precipitating ice crystals through the atmosphere. So the big result here is that we wouldn't see that if the clouds were composed of very small ice crystals, like was assumed before. So the big discovery here is that, actually the ice crystals grow very large, just like cirrus clouds on Earth at the same temperature, and the water falls through the atmosphere, precipitates down towards the surface. This is an example. So what would it look like on Mars? So if you were standing on the surface of Mars and you looked up while this was occurring, you could see through these clouds, you could still see the stars, and you'd see the odd shimmering, sparkling ice crystal that's falling down. If the moon was up, full moon, you'd see some moonlight reflecting off the odd ice crystal here and there. And that's very common in the Arctic. It's called diamond dust. And so in the Arctic, you stand outside, you see the odd ice crystal coming down out of thin air. And so that's what it would look like on the surface of Mars. And this is an example of some measurements at Eureka Weather Station. This is on Ellesmere Island in the Canadian Arctic, and when diamond dust was actually occurring. So this is lidar again, and you can see the enhancement in this signal. Ice crystals were forming at a height of about 7 kilometers, 6 kilometers, and you'll see the fall streaks down to the surface. So this is while diamond dust was occurring on Earth. So a very similar process. In terms of water, in the water cycle, it's very similar to the Earth's atmosphere where the temperatures are very cold. Now the question is whether this is important, whether this affects the hydrological cycle. So the whole idea was to understand why there's so much water under the surface, how it got there over geological timescales, over millions of years. What are the processes that are important? So is there a hydrological cycle? Does it snow like it does on Earth? Does this precipitating ice crystals reach the surface? And well, here's an example where they did. So earlier in the night, 3 a.m., 3:30 a.m., cloud at the ground, fog at the ground, and a cloud between 3 and 5, 6 kilometers. And then later on in the morning, 5:30 a.m., you see the clouds dropped all the way to the ground. You have a fall streak here going all the way to the ground. And so this is our evidence that it does snow on Mars, so that the ice crystals do drop all the way to the ground. So there is a hydrological cycle, and precipitation is part of it, as on Earth. Okay, so again, I just wanted to mention that, so this is what we're trying to understand, the ice under the surface, how it got there. And now, to understand this, to look at the geological history of water on Mars, we have to run computer simulations. And so now the computer simulations had to be changed to include the process where the ice crystals are large enough. And this really changes how water is moved around on Mars over millions of years. And so what the implications of that will come out after the studies are redone in simulating the atmosphere of Mars with large climate models. And okay, and to put this in context one more time, I'll just compare it to Earth-based measurements again. And so this graph just shows the temperature estimated in the atmosphere of Mars. This is a computer model simulating the atmosphere of Mars by Peter Taylor in the Department of Earth and Space Science and Engineering at York. And so where the cloud formed at 1 a.m., the temperature is about -63 is our estimate. And well, that's interesting because that's where we do our best work. So with an airplane called the Egret, we study cirrus clouds at heights of about 15 kilometers in the tropics, for example, where the temperature is about -60, -70 degrees. And so we have a lot of samples of ice crystals and clouds at that temperature range. And we normally fly with another airplane, like a Twin Otter or a King Air, with a lidar, which is very similar to the Phoenix lidar, which became the prototype of the Phoenix lidar, beneath the cloud. So one plane's mapping the cloud, the other plane is flying through the cloud, and we can make a direct comparison of the measurements. And this is one example. This is above Adelaide, Australia. So at the top, this is a lidar measurement as a function of distance from the airplane, showing the outline of a cirrus cloud. There's some fall streaks here. They're hard to make out, but that's what they are. The dark line is the path of the egret airplane through the cloud, and it's sampling the ice crystals, and this is what they look like, the ice crystals within the cloud. So most of these are about 2/100ths of a millimeter across, the largest ones. And there's a tendency to have these columns. The crystals are shaped into columns. They're hexagonal and columnar. And they start out in these bullet rosettes, they're called, because the columns grow out from a central core, and they break apart. But a lot of the ice crystals are just irregular in shape. But this is what they look like. And the main point here is we do have measurements with a lidar, same as the Phoenix lidar, and of ice crystals at the same time. And this allows us to compare the actual ice water content, the mass of water per unit volume, to the measured extinction coefficient with the lidar. So on Mars, our measurements were usually in this range of 0.1 per kilometer. And that, for Earth-based clouds at the same temperature, that's about 1 milligram per cubic meter of water. So we have a pretty good estimate of how much water is actually in these clouds on Mars. And so we have 1 milligram per cubic meter. If we integrate that, sum that up through the depth of the cloud over 1 kilometer, that would be about 1 gram per square meter of water. Not very much. If you took it out, if you took all the water down to the surface as liquid, it would have a depth, a thickness of only 1 micron. That's 1/millionth of a meter. So it's not much. But it's about the same as water you see in these high wispy clouds on Earth. And these clouds have a very important impact on our climate here. And so it's not that insignificant. And we can compare that to the water cycle on Mars. So this is this shows the total amount of water in the atmosphere that was measured from a satellite. So over the course of the mission at our latitude, while we were observing clouds, the total amount of water in the atmosphere decreased from about 60 grams per meter squared down to about 20. And it was decreasing by 1/2 of a gram per meter squared, or 1/2 of a precipitable micron per day. And we see twice as much as that in the cloud, actually. So the amount of water in the cloud is large enough to be very significant in the hydrological cycle on Mars. So what we've found is evidence that the clouds and the precipitation are very important for the geological history of water on Mars. And so that's what we learned. There are other instruments on the spacecraft. And so looking back at some of the images taken from the camera, we found some where we could put a series of images together into a movie and look at the clouds going by. So later on in the mission, we did start to see the clouds with the camera. And some clouds drifting past. And I'm circling one where you can see some precipitation from the cloud as well. And it's happening very quickly. And so what happens here is the cloud forms, and then you see the bottom kind of drop out of it. And, okay, here it goes. I'm just repeating it there. Now, I don't know if you can see that. So those must be very large ice crystals for it to drop out just like that. And I've never seen any, okay, this is sped up in time. So you can see this happening on Earth. It's called virga usually. That's what pilots call it. Ice crystals below the cloud before they sublimate. So we do see this in the images as well. And okay, so what we learned basically, there's a lot of turbulence through the day in the atmosphere. So dust and water vapor mix up to a height of 4 kilometers during the day. At night, ice crystals form. A cloud forms at the top of the boundary layer and at the bottom, and then it precipitates down to the surface. Sun comes up, and it repeats itself again, mixes up to the top and then back down to the surface. And when it lands on the surface and sublimates away when the sun comes up and heats the surface, some of that vapor will go and stick on the water below the surface, that ice table below the ground. So in due course, we continue to study that, but we're going to have to use chambers now. We can't just go back to Mars and repeat the experiment and change it that often. So the next stage is trying to recreate the process within a chamber in the laboratory. All right, and okay, I'll finish with a sad slide. So we kind of hoped, we knew that the spacecraft was not designed to last through the winter, so we landed in the middle of summer. We're in the Arctic region, and we lasted for 5 months there. The mission was supposed to only go for 2 months, but we lasted as long as we could. We kept it going, but eventually there wasn't enough sunlight. It's a solar-powered spacecraft. There wasn't enough sunlight, so the spacecraft had to hibernate. And we were hoping, so we went through the Martian winter hearing nothing. We were hoping that it would survive the winter, but it wasn't designed to. So the temperature's down to negative 150 or below, and so this would cause some components to crack. So in 2008, here's our nice, shiny, bright spacecraft, brand new. Here it is in 2010, same time. And we were hoping it would come alive, and it looks like the solar panels fell off. Or they would have had a lot of frost on them, and it probably collapsed. And so the mission is definitely over. And I'm afraid I have to leave it on that sad note. However, we did discover something, and I'll stop there. Thank you.